So this is some A2Pure, and it is differentiation of trig functions. So the first thing to note is if you differentiate sine x, you get cos x. If you differentiate cos x, you actually end up then with minus sine x. So those are two that you will need to learn and know how to use. First of all, then, if we consider y equals sine 3x. This is actually a function of a function. We would have done this a couple of units ago, and this is more generally what functions of functions are used for. So I'm going to let u equal 3x. That means y equals sine u. Dy by du. Then if I differentiate sine, I get cos. So that gives me cos u. Du by dx equals 3. And dy by dx, as we know using the chain rule, is dy times du times tu times dx. Dy by du is cos u multiplied by 3. Don't be getting that mixed up in with the angle. And so that's going to be 3 cos, and change the u back, 3x. You end up getting used to the pattern of these, but you need to know how to kind of work your way back to it if required. It's similar then for y equals cos 3x. If you were to differentiate that, I'll just do that one on the one line. If you differentiate cos, you get minus sine, remember, so it's going to be a negative, and then the 3 again would come out the front, so it's minus 3 sine 3x would be that differentiator. In general then is down at the bottom, so if you have sine nx, where n's any number, it's going to give you n cos nx. I hope that's reasonably obvious. Let's look at the one above. Say for example it was sine 5x, you're going to end up with 5 cos 5x and so on, and then the cos one is down there as well. Now if we take a look at sine squared, sine squared, if you didn't already know, now is as good a time as any to learn. It's actually the same as that. That's what sine squared means, and we now have a bracket, so we're going to let u equal sine x. So that means y is going to be u squared. Dy by du is going to give me 2u. Du by dx, if I differentiate sine, I get cos. Dy by dx then is going to be dy by du times du by dx. Dy by du is 2u. Du by dx is cos x. U, of course, back up here is sine x. So the answer is going to be 2 sine x cos x. Now we'll get onto this a little bit later on, but again there's a pattern for these sort of things. Whenever you do sine cubed, you get a wee bit of a pattern and things like that. And again, if you look then kind of down below, you get your general pattern for it. Y equals sine x is n sine to the minus 1 n x cos x. If, for example, it was sine to the power of 6x, that would end up giving us 6 sine the 5x, because you're taking 1 off, times the bracket differentiated then, which is going to be cos x, and a similar enough then we pattern for the other ones. Let's take a wee look then at tan x. Tan, we hopefully know, is the same as y equals sine x over cos x. This is a quotient. U is sine x, v is cos x, du by dx, what do you get if you differentiate sine? You get cos. dv by dx, what do you get if you differentiate cos? You get minus sine. Subbing it into our formula for the quotient rule is of course v du by dx minus u dv by dx. So v times du by dx is cos times cos. I hope you see that. So that's going to give us cos squared x. take away u dv by dx, so that's u times dv by dx, so that's sine x times minus sine x, that's going to give us minus sine squared x, but that's a minus minus, so it's plus, and that is then all over cos squared x. We know what that is. Cos squared plus sine squared is always 1, so we end up with 1 over cos squared x. And what we just learned in our recent trigonometry section was that, sorry, my pencil's just broken here, let me grab another one. There we are, they should be up and running again here. 1 over cos squared x then is just the same as sec squared x. So that's a way of differentiating tan x, but to be honest, it's one again that you should know. Let's take a wee look at the next bit. That was just more space to do what we needed to do, and here then are the other 4 that we needed. So if you differentiate tan, you get sec squared. If you differentiate cot, you can actually do it the same way. Cot, of course, is 1 over tan, so you would write that then as cos over sine. If you do the quotient rule, you get it from there. Sec, if you differentiate, you get sec x tan x, and cosec, if you differentiate, you get minus cosec x cot x. Let's take a wee look at some examples, and we will see how we go. So y equals tan 5x. I'm going to let u equal to 5x. That means y is tan u. dy by du, we just did it in the previous page, is going to be sec squared u. Du by dx is going to be 5. dy by dx is dy by du times du by dx. So it's going to be sec squared u times by 5, and that's going to give me 5 sec squared 5x. Again, keeping the same pattern as before with the sine and cos stuff. I hope that makes a reasonable amount of sense to people. Y equals sec 3x. Same again. Y equals sec u, because I'm going to let u equal to 3x. Du by dx is going to give me 3. Dy by du, so you might need to look back a couple of pages, but if you differentiate sec u, you get sec u tan u. Dy by dx then is going to be dy by du times du by dx, so it's going to be 3 sec u tan u. Subbing back in, then we're going to get 3 sec 3x tan 3x. Next one. Find dy by dx, y equals cot x over 4. Y equals cot u. Because we're going to let u equal x over 4. The way I'm going to write that is obviously a quarter x. What do you get if you differentiate cot? Again, you might need to look back to remind yourself. It's minus cosec squared u du by dx. The x is just going to disappear, and we end up then with a quarter. Sorry, I've made a mistake here. That's dy by du, of course. Apologies. Dy by dx then is going to be this times this. Dy by du times du by dx. We're going to bring the quarter to the front. So it's going to be minus a quarter cosec squared u. And subbing back in my u, then I'm going to get a quarter cosec squared x over 4. You don't necessarily need the bracket there, but it's just so you can see where we're getting it from. Next one, y equals cosec x squared. Now note where the squared is. If the squared was here, that would be the whole function squared. That was, again, if you look back a couple of examples ago, but no, this is actually set up like this, and this is the way we're going to deal with it. So I'm going to go for y equals cosec u, where I've let u equal x squared. Du by dx is 2x. dy by du, what you get if you differentiate cosec u, you get minus cosec u cot u. Dy by dx then, dy by dx, we're using the chain rule, aren't we always? Dy by du times du by dx. So we have a minus this times by the 2x, so I'm going to take the 2x to the front, minus 2x cosec x squared cot x squared, changing back my u's into your x squareds. They can be a wee bit ambiguous. I like them much nicer with a bracket around them, but that wouldn't be compulsory. Next example is a reasonably classic example that you'll see all the time. So y equals sine to the power of 4x. Again, you hopefully saw a couple of examples ago that that's the same as sine x all to the power of 4. So I'm going to go y equals u to the power of 4 because I've let u equal sine x. Du by dx, if I differentiate sine, I get cos x. If I differentiate this, I get 4u to the 3. Dy by dx then is dy by du times du by dx, so it's going to be 4u cubed cos x, and that's going to give me 4 sine cubed x cos x. Again, I hope you see what we've done. Remember, sine cubed x is the same as sine x all to the power of 3, and so your final answer there. Again, if you look back a couple of pages, you will see the wee pattern there where that kind of 4 comes to the front and so on. It's a reasonably standard one, and I hope you understand where I've got it from. Example 6, we're getting there slowly but surely. Y equals cosec x, and that's all to the power of a half. I'm going to let u equal cosec x. Du by dx, and if you differentiate cosec x, you get minus cosec x cot x. Y equals u to the power of a half. Dy by du is going to give me a half u to the minus a half. So this means dy by dx is going to be dy by du times du by dx. There's a minus there and a half, so let's take those in out to the front. So minus a half, and then that's going to be cosec x to the power of minus a half, and that's times cosec x cot x. So how can we tidy this up? We just need to be careful. There's actually a wee bit of indices involved here with minus a half. Here we have cosec x to the power of minus a half. Here we have cosec x, and that's just to the power of 1, obviously. So if we have two things with the same base, we can add the powers. Minus a half plus 1, it just gives us cosec x to the power of a half. So it's cosec x to the power of a half. We can put our wee half in there or put our square root back in. That's fine. That down is times cot x. I'm happy enough with that then as our final line. Example 7, another couple to do here. Y equals 1 over tan cubed x. Couple of ways of doing this one, I suppose. I'm going to go for y equals tan x to the power of minus 3. You could use a quotient rule there with u as being 1 and that being the other, but that's fine. What am I doing? I'm going for u equals tan x. Du by dx is going to be, well, you got to differentiate that. You get sec squared x. Y equals u to the power of minus 3. Dy by du you differentiate that, you get minus 3u to the power of minus 4, and we want dy by dx, which is dy by du times du by dx. So that's minus 3u to the minus 4 multiplied by sec squared x. There's a minus there, so it's going to come out the front. We're actually going to have a quotient here. So that's going to be sec squared x, and then with u to the minus 4, so u is of course tan x, so we have tan x, so tan x to the power of 4 is going to go on the bottom, but the 3 of course isn't to the power of minus 4, so it's going to stay then on the top like that. Slightly confusing there with just a wee bit of algebra. I hope you can follow then what's going on. Next example, starting to get slightly messy here, but we should be okay. What will I do? I'll go for y equals cos 3x all squared. I'm going to let u equal cos 3x. dy by du. We've done this one recently. This is actually a function of a function within a function, if you want to think about it like that. But we're just going to do this all in one big lump. So that cos differentiated gives me minus sine, so it's going to be minus 3 sine 3x. Y is u squared. dy by du, then it's going to be 2u. That means dy by dx is going to be dy by du times du by dx. Minus 3 times the 2, then we're going to go for a minus 6u sine 3x, and then changing our u back again, minus 6 cos 3x sine 3x. 2 to go. We're doing well. Example 9 then. Y equals x cubed sine 4x. This is one I'm hoping you're able to spot. This is going to be a product rule one. We know how to differentiate x cubed, we know how to differentiate sine 4x. So we're going to use the product rule and do them separately. We're going to let u equal x cubed. We're going to let v equal sine 4x. du by dx is very straightforward. That gives us 3x squared. dv by dx is actually a function of a function, but we're going to leave that bit out. If you differentiate sine, you get cos. If you differentiate sine 4x, you get 4 cos 4x. I hope you follow that. dy by dx then is u dv by dx, so it's going to be 4x cubed cos 4x plus v du by dx, maybe the other way around, but that's okay, plus 3x squared sine 4x. You could take out a wee x squared there as your final line, but I don't mind. I'm just happy enough to leave it like that. On to our final example. Again, I hope you can spot this one. This is a bit of a palaver, but we'll get there with it. This is going to be a quotient rule, obviously, but that top one requires a wee bit of work. So we're going to let u equal sine cubed 2x, and we're going to let v equal x to the power of 4. I'm going to search back a wee bit for this one. Differentiating this is actually a function of a function of a function, even in itself. It's very, very like our example 8. Let's take a wee look back at our example 8. Cos squared 3x. We did our kind of function of function, worked our way through, and ended up then with that. I'm not going to do that again, but the way you do this is to look at example 8 and use that method. If you differentiate, you get du by dx. Again, take my word for it and try it yourself. 6 cos 2x sine squared 2x. So again, example 8 is how you get that one if you follow that method. dv by dx then is going to be 4x cubed. dy by dx equals, what does it equal? V du by dx. We're going to do this times this. So 6x to the power of 4 cos 2x sine squared 2x. Take away u dv by dx, so it's 4x cubed times this. It's supposed to be a cube there, so you can still see everything. And that's all over v squared. So that's easy, that's just going to be then x to the power of 8. So how do we start to tidy up this incredible mess? Let's see, there's an x to the cube that we can take out here, there's a 2 we can take out here, and then there's actually a sine squared 2x that we can take out here. So let's factorize this out. So there's a 2 x cubed we can take out, and then a sine squared 2x. This is nearly the sort of thing you're better doing backwards, so you can see what way it's actually supposed to be working. This times what is going to give me this. So it's going to be 3x cos 2x. This times what is going to give me this. So it's going to be 2. The x cubed is already there, and then it's just going to be sine 2x. That's all over x to the power of 8. One more line and we should be there. There's an x cubed here, which is going to go with that, and that gives us an x then to the power of 5. And so our final line, if you're still with me, sine squared 2x, round bracket will be fine there if you wanted, cos 2x minus 2 sine 2x, and that would be all over x to the power of 5.